Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Did you keep the cap?
Yep.
All right, I'd like to introduce the second dynamic languages talk for this session. Without further ado, I'd like to return to Dr. John Goff, who will speak about dynamic languages on the CLR.
Well, thanks very much, Mark. I must say I was really interested in the previous talk because it covers a kind of different perspective from the areas that I want to talk about, but I keep being overwhelmed by these floods of nostalgia as somebody who worked a lot on coroutines back in the 80s, I guess, and first half of the 90s. I did a whole lot of Modular 2 compilers. Modular 2 has coroutines built in, and there's a guy called Mirren Livney at the University of Wisconsin made this really good simulation environment, which was pretty widely used by people who were simulating big databases, and IBM and Boeing and all these people were using his stuff, and it was all written in Modular 2. And most people write Modular 2 programs with 2 or 3 coroutines. He wrote stuff with hundreds of coroutines, and he broke every Modular 2 compiler in the world, of course, because he went where nobody had ever gone before. And I sort of spent a bit of time with him and actually made our compiler robust enough to run as framework. So coroutines are great fun. They're one of my favorite features. But okay. Well, I want to talk first of all about what I mean by dynamic languages and what the implementations are. This project started off and we wanted to, if possible, dig out the issues that are generic to the implementation of dynamic languages and find ways of propagating information in the community so that we have solutions to those. And that's still what I'm on about. The languages that I'm interested in are particularly the languages that are used for scripting, but the issues are similar to those of other non-imperative languages. The functional languages share a number of the same issues. The one thing that I guess makes them a little different is the dynamic nature of the name binding, so that you don't have the luxury of the compiler being able to say this name, whenever you reach this particular program point, this name means this method, and therefore we generate code to call it. And the other thing which certainly the scripting languages have, which perhaps not the functional languages share, is that because they're widely used for scripting, they tend to have very powerful pattern matching features. And in fact, one of the most widely used of them, Perl, is started off with the intention of just doing pattern matching, really, and the rest of the Christmas tree that now surrounds it is sort of grew over the years. The standard way in which these languages are implemented is you have they're very seldom implemented by directly interpreting the source code. So they're compiled languages, but they compile either into some kind of bytecode form or some abstract syntax form, and you have an interpreter which is invariably unique for that one language that either traverses the abstract syntax tree performing the execution or interprets the bytecodes. I guess one of the other characteristic things of the particular languages is that they all have some element of dynamic compilation, in the sense that you have something equivalent to an eval, and you typically have this interesting situation where you have execution of the program during compilation, and compilation taking place during execution, so that you have a sort of more interesting operating environment. A number of languages that fit into this particular category were part of the famous Project 7 that Microsoft got together in 99 and 2000 prior to the announcement of the CLR. The object of the project was to demonstrate the multi-language capability of the framework. And so there was a wide range of languages there. There was a first cut at Scheme, there was COBOL, and I guess you all know the story. As it turned out, the experience with the scripting languages that were part of Project 7 was not a happy one. And in fact, if you look at Damien Watkins' book called, somebody help me, what the hell's Damien? It's there, Programming in the .NET Environment, yes. There's a number of appendices that were contributed by Project 7 people, and I wrote an appendix which said, you know, the CLR is wonderful and I love it and I do it again. But there's a chapter on Python and one on Perl, and they're very downbeat. The results that were got at that stage were difficult. The performance issues were difficult. And as a result of that, it's become the common wisdom out there in punter land that the CLR is no good for languages of this kind. And that was the kind of accepted wisdom, and nobody really challenged it, I guess, until Jim Huguenin had did the first prototype via Python and showed that that isn't necessarily the case. It's clear that there are issues involved in the implementation of dynamic languages, but that is true whether you, in performance issues, but that's true whether you do native code implementations or whether you do implementations on top of the JVM or the CLR or any other method. So the interesting question from my point of view is, what are the things that are intrinsic to the level of abstraction at which you have to work with CLR that need to be unpacked? So we had a look at Perl, and the other constraint that I should mention is that I'm only interested in verifiable code, right? If you're not doing verifiable code, then you have to say, well, why are you doing it on the CLR anyway, right? I mean, there's still a reason. As I mentioned yesterday, I've done an unverified compiler because it's there, right? But if you're seriously going to run scripting languages on the CLR, you want to do it in such a way that you can run it, say, as stored procedures for SQL. You know, you have to be verifiable, or there's no point in going there. You may as well just, you know, fork and exec and run the external process. So what we discovered, and we didn't implement Perl. Perl is huge. Perl is a monster. You really don't want to go there unless you want Perl very, very badly. But we looked at the things that might be troublesome, and we sort of hooked together a breadboard implementation. And I think the conclusion we came to is you can do all of Perl in a verified way, even including the bits that look as though you shouldn't be able to do them verifiably. No question that some of these things are inefficient, but you can do them. However, I don't think that Perl is very good. I don't think Perl is a very good example to try and unpack these generic issues that we want to solve to answer the question about whether or not you can do languages of this class on the framework. So the current project, the one that I'm reporting on now, had tried to factor out those common issues that have to do with the class of languages to try and find implementation techniques that were widely applicable. As it turned out, I think that was a little overambitious. There are certainly issues which occur in these languages which, if you find a good solution to, are applicable over several languages. But the idea that you could somehow find some sort of common AST form that you could transform all of these languages into, and then you just needed to implement that AST and bingo, you solved everybody's problem, was a little naive. It turns out that one of the things that's dynamic about dynamic languages is that they're all different. They all have subtly different semantics. They have different issues, like some have coroutines, some don't. They have different scope rules and different rules about the persistence of variables and so on. So I guess that we have abandoned the idea of coming up with an implementation framework that will do for multiple languages, but we're still interested in finding techniques and sharing techniques and propagating in the community all of those good solutions which are helpful to all of the people working in this particular part of the discipline. Okay. Well, what are these implementation issues? Well, there's a few of them, and we heard about one, which has to do with mapping to the threading system and also the issue of coroutines. And I know I already ranted on about coroutines, but coroutines are interesting for other languages as well. If you have a look, because they're a really neat way of doing proper iterators, the language Sather, if I've pronounced that right. Any Berkelians here? Sather is an object-oriented language, and Sather has iterators, but they're not first class. In fact, they're not even worth having, in my opinion. But Sather K, which is the Karlsruhe variant of the language, does have proper iterators where iterators are first class, and they require coroutines for their implementation, and they're of course much more useful than, as I say, the regular ones they're really only syntactic sugar. There's the idea of the efficiency of method dispatch, which is always been seen as a big issue. It's actually, in my view, not intrinsically a big issue. Method dispatch for dynamic languages is always going to be slower than just ordinary invocation of a method. But that's true for native code implementations as well. So we're not saying, you can make it run as fast as C++. The question is, can you make it run as fast as the C interpreter, an interpreter written in C? And there's the various scope and visibility models, which require sort of handcrafting for each language, and closures, which are a problem which is of interest very much to the functional language people as well. Yeah.
Method dispatch is inherently going to be slower. I can imagine static dispatch as being the fastest. V-table dispatch is slower than static dispatch. But I could imagine that you could, as your model, try to achieve a V-table dispatch speed for these languages. But what are the problems that prevent you from doing this?
Okay. Yes, I really do talk about that in a later slide. But the issue is that if you have if you have truly dynamic binding of names to methods, then you may be stuck with a situation where you have to look up what the method is every time. Now, if that is true for a CLR implementation, it will also be true for a native code implementation. So you're not necessarily worse off. And the issue is, first of all, correctness. But once you have a correct implementation, you have all of the machinery available for taking account of the fact that these references, these bindings may be dynamic, but they tend not to change. So you've got caching issues.
But you could imagine where you have to look it up the first time, and then as long as nothing changes your type system, you don't have to look it up again until you introduce a new type.
Well, that's sort of phase 2 of the project. Phase 1 is make the semantics correct. Phase 2 is to take all of the machinery of algorithms and data structures theory and wallop on this thing to beat it into shape. In fact, the Sabre implementation does this mainly because it's got a multiple inheritance framework, and I'm not quite sure whether does Eiffel use caching of in method dispatch. Sabre just works on the assumption that unless you find out to the contrary, the method that you call is the same one as you called last time. You know, I mean, really simple-minded, but effective on average. Anyway, no. Okay.
Small dog works this way. Small dog virtual machines. The 1984 paper on the small dog VM introduced this kind of cache, the inline cache on method calls.
Sure. But I mean, it's never going to be as fast as a static call.
Yeah.
Okay. And worse than that, of course, all of your optimizations are not going to work. It's not just the speed of the intrinsic speed of the call. It's the fact that you can't do classical optimizations on it. All right, well, closures are an issue. Let's not talk about that anymore. Well, let's talk about it briefly. There are various methods by which closures are done in the functional language community. Some of those are not really very easily applicable to the framework, but that's still an issue. There's no easy way of doing this efficiently, I don't think. Dynamic code generation is, as I said in the introduction, part of the standard fare for dynamic languages. And I think that the story here is a good one in that we've always been able to do it in the managed frameworks on the CLR, and the lightweight code gen facilities of WIDBE should make this much easier. We have actually done experiments with simply with a kind of heavyweight approach, which seems to work reasonably well. We have, in fact, three ways of doing this, really. There's the reflection emit, which has always been there. There is, and we experimented with just simply using our PE file writer, which just writes to a memory stream which you can immediately load without actually it ever touching even the disk cache. And it seems to work quite well. But I think the method of preference going forward is always going to be lightweight code gen. That's what I just said. I already talked about most of this. Efficiency of subroutine calls is problematical, but it's not clear that it's any more inefficient in this a particular context than it is for a native code implementation. But there is this issue about the static, the bindings are theoretically dynamic, but in practice they change very slowly, so that some kind of inline cache is an obvious optimization to look for. And I'd now like to talk particularly about the work that I'm doing going forward. We're now doing an implementation we're starting on an implementation of Ruby. Ruby is our language of choice for a couple of reasons. First of all, it's one that we were not aware of anybody else doing, because we didn't, for example, want to do Python, given that IronPython seems to be doing pretty well. We knew about the Lua implementation, and there's a PHP implementation also from this particular hemisphere, and Ruby's a really nice language. It has a fairly big, for those of you that don't know about it, it's a object-oriented language. Everything's treated as though is an object. It has a fairly large following in Japan, which is where the language originated. It has a reasonable following in the rest of the world, and the followers are a fanatical band, as you tend to get in this space. But intrinsically, it's an interesting language. It has all of the usual stuff you'd expect. It's got good pattern matching facilities. It has the ability to, and it's sort of dynamic, and you have the possibility of adding singleton methods to individual objects. So it involves some of the ideas that we heard about yesterday from one of the other speakers to do with kind of this idea of having methods, new methods attached to individual objects rather than to all of the existing objects of a particular class. That suggests that using the common type system is not a good way of implementing this, and at the moment we believe that we will have only a single class as far as the CTS is concerned, which will be Ruby value, and there will be the usual semantically determined pattern of lookup, so that when you call a method you say the object asks itself, do I have such a method? If not, does my class have such a method? If not, does the for the time being superclass have the method, whoever is my superclass at the moment? So the type system of Ruby is described, I mean, this is a concept which applies to other languages as well, but within the Ruby community they have this nice notion which they call duck typing, which is it's a kind of compound pun, because it sounds as though it ought to be duct tape, which, as you know, holds the universe together. But it comes from the saying that if it flies like a duck and it quacks like a duck, then it is a duck. And this is the nature of the type system. A particular object belongs to a type if it happens to, at that moment, at that particular program point, if it implements the operations of the type, then it is that duck. So it's kind of cute. It's nice language. Okay. The standard implementation of Ruby has has an interpreter which traverses an AST, and did I mention it on the last slide? This language has first-class continuations, right? This is a big issue. It has continuations. That's the other reason I wanted to do Ruby, because it's a challenge. Okay. Ruby's got a fairly large grammar. It's about roughly, I haven't counted them, but there's roughly 1,000 productions in it. So it's a big grammar, and it's got a bottom-up parser. A bottom-up parser in the standard one, which is not encumbered in terms of copyright to prevent us from using it as, for example, if it was restricted in some way. So the design outline at this stage is that we will use the production set of the existing grammar to produce an AST. Our AST will be different, but and we are going to be producing bytecodes, which we will then interpret as part of the execution. And we debated it for a while because I'm a great fan of Hans-Peter Mossenbock's COCO-R top-down parser generator, but in the event we're using a bottom-up parsing. We're not quite clear whether we'll be using generics in the bytecodes that represent translated Ruby programs, but definitely the framework itself, the implementation, is already locked into a generics-capable framework, which is one of the reasons that I was interested in asking Joel about getting compatible generics on Rotor, because we're sort of getting locked into the would-be syntax. Continuations are really challenging. At the moment, the only way that I know of implementing continuations in a way which would be verifiable on the standard platform is one that's currently being explored by Joe Marshall at Northeastern University. If anybody's interested in how that works, I'll take it offline because I don't want people to glaze over. But it's a technique which is known already from the functional language community, but not one of the widely used methods there. So it's a bit of a blast from the past. But it looks like about the only way to go to do that. Okay. Now, we are serious about this compiler. We're not, when we were investigating Perl, we were fiddling around with little snippets of code to see if we could get particular things to work. We are intent on building a serious implementation this time. We don't want to throw one away. We want to get it right. And also because our intentions are to contribute knowledge and tools to the community. When we need something in the project, we're building it. And one of the things, the first of those things actually hit the deck last week, and we keep seeing posts to news groups saying, is there a YAC lookalike that produces C#? And actually there was one that we came across, and it was which was designed to be a tool for teaching about parsers, and it worked pretty well on little toy grammars, but it failed completely when it was confronted with this monster of ruby.y, and it took about an hour and then produced bad tables. So my colleague Wayne Kelly has written Garden's Point parser generator, which runs at a speed comparable with YAC. It is completely unfazed by 1,000 production grammars, and running it alongside YAC just with semantic actions that just simply log the reductions on the 1,600 test programs of the Ruby test suite. It's reduction for reduction identical to YAC. So we think it's ready for prime time. That's not to say it doesn't have bugs, but it's at least sane, and as I say, it's fairly quick. Okay. The other thing which I already mentioned yesterday was per WAPI. Here's some, per WAPI has been out there a little while. It's getting a little more robust. This is using per WAPI to bootstrap our component Pascal compiler, writing the textual IL files, 2.9 seconds. That's for, I don't know, 100,000 lines of code, maybe 3 seconds using per WAPI, 7 seconds if you use IL. And I did check the would-be IL-ASM is a bit faster than that, but it's still pretty quick. It's 54 files.
54 files and 54 binaries?
Yes.
Or one single binary?
No, 54 separate binaries.
Oh, so IL-ASM invokes 54 times.
Yeah. The problem is, Serge, even if you ran your program at infinite speed, we're doing 54 process startup times. You know, it's a hard ask. Okay, the other thing that people complained about with per WAPI, other than the fact that it had bugs in it, was that there was no documentation because Diane Corney, who wrote it, doesn't do words. Anyway, so here is finally the release notes manual, and it's about 37 pages of PDF. And which we put together. It's got diagrams which explain the internal structures. For example, that's the abstract representation of types. Black things are abstract. The white ones are extensible types, and the grey ones are sealed classes. Okay. And I'm also going to be releasing, hopefully within a short while, a C# version of my old bottom-up tree rewriter, which is kind of neat. And I'm not sure whether is this machine connected to the internet, Mark? Oh yes, there it is. Gardens Point Parser Generator. That's the page. You can download it from this link here. There's some stuff on how to use it, and it requires Beta 2, version 2 of would-be. And that's the end of my talk. Thanks. Any questions? Joel.
Cross-language interop. Are you going to be tackling that in Ruby.net? You mentioned
hell yes. There's all this great stuff in the base class library. I don't want to have to write that in Ruby.
The other way, if you're embedding
like
C# to Ruby embedded classes and fun things like that.
Well, I guess so, but we've done no design work on that. I mean, you know, you have to be able to invoke it at least. But yeah, haven't. That's asked me in 6 months' time.
Or probably will involve quite a lot of runtime code generation for that.
Yeah, sure.
I'm very interested in much more details about this parser generator, but I hope I can find all information on your website. So how you do error recovery, so heavy error productions, and so on. But
well, one of the reasons that I've always preferred good top-down parsing rather than bottom-up is I think that doing error recovery in bottom-up parsers has always been an issue. But, you know, it's a sort of religious thing. But, but there's information there. And the other thing is all of our stuff, in the past we did do commercial software, but right now everything we're doing is open source, and it's a free BSD license, so you can use it pretty much any way you like, non-commercially.
Is this Ruby.net the same one that was in the Google Summer of Code?
No. That was the Mono people who said they were interested in a student over the summer putting together a Ruby prototype, and I'm interested to find out what happened with that. But this is
I think they have some code checked in a CVS.
Yeah. I mean, the problem with all of these languages is it's very easy to do a small subset, when it really is pretty easy to make Hello World run. But that's when the hard bit really starts. Joel?
Any ideas on how to implement duck typing? To kind of get that working from the cross-language?
Sure. From cross-language point of view.
Well, the first part's presumably pretty easy, right? But
it's quite getting the correct semantics within Ruby are not an issue. But there are issues about how to make it run as efficiently as you can. But basically, you have this. You have software that does the name binding according to the semantic rules of the language. And the question is, can you do better than doing a sequence of a zillion table lookups? Coming the other way, I haven't really thought about it. This project is like the space program. You start on a project before you've got the technology to do everything that you're going to need to do. It helps you get up in the morning when you've got this rush of adrenaline and fear about whether you can actually do this stuff.
One thing, you mentioned that you plan to generate IL. Is this when you run the IL? What will happen is the same thing that would happen if you run the Ruby interpreter in the source file, or the process of generating the IL will also interpret what is in the source file. Because in Ruby you can have code inside class definitions, and you can have executable code inside class definitions. Method calls that interpret execution. Execution and compilations are very...
Oh, sure. There'll be a fair amount of dynamic code jam. Yeah. But, we want to generate code as much as possible.
Because Lua works this way also, and the way we did it is the IL. When I compile a Lua source file, the IL I generate has to be executed to do and define the things that were in the Lua source. The actual compilation into IL doesn't do anything. Just translates from Lua to IL. Don't know if you're...
We'd better take that offline.
Any other questions?
sorry, one more. Sorry. A question on Ruby. Does it have the same kind of expando as, say, JavaScript does in the language, or adding...
You mean dynamically adding fields?
Yeah, and or methods.
Methods, yes. Peter.
Hey. So have you actually given much thought to how you would do something like becomes? Like the ability to kind of like dynamically morph your type?
Yeah. The question is how to implement the becomes, which morphs the type. I think that all you're doing is changing the inheritance hierarchy with that. And you know, we've given up the idea of mapping to the common type system. I mean, it's just all you're doing is you're just changing your internal representation. You've got a reference which tells you where to look if you don't bind the name in your own class, and you just flick that pointer so that it goes somewhere else, and next time you do a lookup, you look somewhere else. The real challenge is to do that efficiently. But you know, Ruby is not a language which is, if you look at the source code, you rapidly, the performance is surprisingly good, but when you look at the source code, you realize that implementation efficiency was not a big issue for these guys, because everywhere inside the eval routine, where you're walking over the AST, everywhere where there's a possible continuation point, you've got a set jump. You know, you're actually saving a jump buff at that point so that you can get back there. I mean, this is you know, heavyweight stuff. So and you pay that price whether you call it continuation or not. So yep.
Another question, just to follow up. So, at what level of integration with the CTS are you thinking of targeting? I mean, consuming classes, obviously, I guess that's on the list, but what about extending classes? Extending framework classes?
That's something we haven't designed yet. It'll need a fair amount of glue code to do that. But in principle, you know, it's just an add-on. It's an extra variant of your name binding to eventually go out and, you know, look for something. But I guess you need some kind of syntax hack so that you know that a particular name refers to a base class library name, so you can't fool with it in the way that you would with a regular Ruby. You know, it's different semantics, and you've got to know when you're passing the boundary from your native semantics to the foundation class semantic.
I guess that would probably impact some of your method binding too.
Yeah. Sorry, we're a bit over time there.
It's okay. It's definitely worth it to have some lively discussion. Let's thank our two speakers for these two talks. We are running